Bonjour, everyone. My name is Honn Kao. I'm the project leader for Induced Seismicity research. And in this talk, I will quickly go over three key highlights that our project has accomplished last year, including injection-induced earthquakes monitoring in Western Canada, the Tower Lake Dense Array experiment at a hydraulic fracturing site in Northeast British Columbia, and enhanced collaboration with external partners. We have team members from 4 different GSC offices, including research scientists, the physical scientists, postdocs, graduate students, co-op students, and administrative staff. One unique merit worth mentioning is that we have leveraged a significant amount of external resources to help with our data and research activities. One major advance that we have accomplished last year is a completely redesigned web interface called Quick Review that combines all relevant information in one place to facilitate routine monitoring and research of injection-induced earthquakes. When we open the web interface, the dashboard will give us a graphic overview of the regional activity. And there is a filter option on the top where we can specify the selection criteria. And in this case, I show all the events that we have detected and located in the year of 2025. In total, there were almost 4,400 earthquakes last year. And in addition to the event map, a time series plot is generated to show each event's magnitude. And we can use this to quickly identify the 3 largest events in 2025, namely the magnitude 4.4 event on February 12th, the magnitude 4.7 event on June 11th, and the magnitude 4.1 event on September 29th. The middle plot shows the event count per each day in 2025, and the peak seismic activity were observed in May and July. And many days actually have more than 100 events during the 24-hour period. Whenever possible, our system will try to automatically determine the focal mechanism for each detected earthquake, and their faulting types are plotted in this triangle figure, with each end representing the reverse faulting, normal faulting, and strike slip faulting. And different colors of the dots correspond to different monitoring areas. And finally, this is the earthquake frequency magnitude plot, also known as the Gutenberg-Richter relation. The system automatically calculates, and our earthquake catalog for 2025, as you can see, has a magnitude of completeness of about 1.1, which serves the purpose of regulatory monitoring and research very well. The system also displays detailed technical information about any specific events that we are interested. For example, when we click the largest magnitude 4.7 event, a pop-up window will show up to display the summary of this event's source parameters, including its time, location, and depth. When we click the view detailed link, it will show these technical details in graphics, such as the station distribution, the phase used in this analysis, the numerical values of each source parameter, and the details on how this event's magnitude was determined and its uncertainty range. And below this plot is a table that shows the seismic phases used in this analysis and its contribution to the final solution. On the quick link page, which is this page, we can quickly recognize any link between the seismic observation and nearby injection activity, as well as the distribution of existing faults. Taking the magnitude 4.7 event, for example, again, once we select it from the list of the event on the left, a map will show up in the middle, and a text panel will show up to the right. On the map, the magnitude 4.7 event is plotted at the center. Seismic events that occurred during the specified time window will also plot with the size of their symbol proportional to their magnitude values. We collect injection information from the regulator's online database and plot the location of nearby hydraulic fracturing pads as red circles, and the trajectory of their horizontal hydraulic fracturing wells are plotted as thin lines from the pad, and nearby wastewater disposal wells are plotted as blue squares, and geological faults in the region are plotted as dashed lines, and these are available from the published literature. On the right is a list of the injection wells nearby this event. Based on the relative timing and position of each well, the system automatically calculates the likelihood of each well that is responsible for the occurrence of this event. The one with the highest likelihood is then associated with the event, and its well information is listed on the top. A light blue circle is plotted on the map, with the radius being the distance between the event and the responsible well. And in this particular case, this hydraulic fracturing pad is about 1.9 kilometers away from the epicenter. All the other injection wells in the neighborhood are also marked with dashed lines connecting to the epicenter, and their likelihood are also displayed in the text panel. So now I'd like to quickly switch my gear to the Tower Lake dense array experiment. This experiment is a multi-partner research collaboration to investigate source processes of hydraulic fracturing-induced earthquakes in detail. The dense array is designed to consist of 36 seismic stations over a 6 kilometer by 6 kilometer area with a grid spacing of 1 kilometer around a hydraulic fracturing pad. Among these stations, 3 of them were equipped with broadband seismic sensors and the other 33 with strong motion sensors. The location of this experiment and the configuration of the station distribution are displayed on this map. The target hydraulic fracturing pads had 8 horizontal wells that extend toward the southeast, and the hydraulic fracturing wells aims at the upper mountainy and middle mountainy formations. The dense array were deployed about 2 months before the fracking starts, and the continuous data recording lasts about 2 months after the completion of the fracking operation. The experiment has multiple objectives. In addition to the scientific questions on the source process of hydraulic fracturing-induced earthquakes, we also want to test the new technologies in instrument communication and ground motion sensors. Specifically, we set a very high recording rate, that is 1,000 samples per second, and want to test how the digital signal can be successfully transmitted back to our data hub in real time over a cellular network. And this experiment is a joint collaboration involving companies in the private sectors. Specifically, in this case, is the hydraulic fracturing operator and the seismic instrument manufacturer, and the regulator, as well as the government science agencies such as NRCan and Innovation Solutions Canada. And this slide shows the spatial distribution of the injection-induced earthquakes on the left and the corresponding frequency magnitude relation to the right. To demonstrate the detection capability of the dense array, we compare the earthquake location result based from the Tower Lake dense array. Using the regional network data, we can locate only 307 events, but when we use the Tower Lake dense array data, the number of events increases by a factor of 4. The vast majority of these events occurred in the immediate vicinity of the injection sites, but their occurrence appears to have a time delay with injection timing, which we will be illustrated in the next slide. We also noticed that some events occurred away from the injection wells, and they probably correspond to the proelastic stress from the injections. On the right-hand side is the Gutenberg-Richter relationship. Again, the left plot and the right plot correspond to different data sets. Notice that the scales are very different, and the overall magnitude of the completeness is significantly improved with the Tower Lake datasets. However, the relative occurrence rate between the large and small events appears to remain unchanged. And this observation suggests that the dense array data can be used to derive the correct Gutenberg-Richter parameters, despite most of the additional events have small magnitude values. In this slide, the left panel shows the comparison between the seismic events and the hydraulic fracturing operation as a function of time. We noticed that there are a small number of low magnitude events that occurred outside of the hydraulic fracturing window. So they probably correspond to the background seismicity in the area. The hydraulic fracturing operation has the injection volumes that we plotted as the daily volume as these blue bars, and they correspond to the occurrence of the injection-induced earthquakes remarkably well. And this is, again, a very clear evidence to suggest that hydraulic fracturing has caused sufficient stress perturbation to the immediate neighborhood that in turn induced many local earthquakes. At the same time, hydraulic fracturing operation, there were active wastewater disposal wells in the area. And it may be possible for some of these wastewater disposal to contribute to the stress perturbation, although we do not have enough information to estimate their precise geomechanical effects. And when we zoom in to the time window of the intense hydraulic fracturing, we notice that the induced earthquakes show a gradual ramp-up activity trend in both number and magnitude with respect to the start of the fracking. And after the occurrence of the largest event, the activity actually dropped quite significantly, both in number and magnitude, when the operator modified their injection operation. So this is a very good example to show that how real-time monitoring works for the operator to implement operational adjustment that can effectively mitigate the induced seismic risk. On the right-hand side, we show the focal mechanism of two representative events. Both show very clear strike-slip faulting mechanism. And in fact, the majority of our solutions show strike-slip mechanism with the compressional axis in the northeast-southwest direction. And this observation is very consistent with the tectonic stress regime reported for this region. It also suggests that the source process of injection-induced earthquakes in this region is very likely related or even somehow controlled by the loading and release of tectonic stress. So in this final slide, I'm showing you a few highlights about the research collaboration that we have accomplished with external partners. First, we signed two research agreements, one with BCER and the other with BC Oil and Gas Research and Innovation Society, to establish high-quality, long-term monitoring capability for induced seismicity monitoring in Western Canada that have regulatory implications. And these agreements covers many areas of collaboration, including real-time detection and location of induced events, consultation on IIE-related seismic hazards and risk issues, and targeted research on key knowledge gaps identified by the regulator and the industry. We also conduct joint fieldwork to service induced seismicity monitoring network in Northeast British Columbia. One service trip was completed in summer of 2025 and another one in February 2026. We have now updated all our networks communication to the latest cell-based technology. And finally, we are glad to report that BC Hydro decided to use the seismic velocity model published in one of our latest papers for their ongoing site characterization work at the La Juhua Dam. And their selection is based on the model's merits, including improved datasets, proximity to the sites, and the explicit uncertainty estimates. And here is our contact information, and I thank you for your attention.